Okay, so let me just remind you what we were talking about on Tuesday, and then I'll give you some definitions so that we have everything in place. Um, and let's see. So basically, what we were doing is just to talk about situations where you can define these two matrices and that gives you some useful information. So remember, like the setup is that we have two matrices that multiply to the zero matrix. And once you have those two matrices together, let me see where it was. Yeah, once you have these two matrices together, you can, which I call A and B, then you can construct this new matrix, which is called the Laplace matrix. Well, at least that's what I'm calling it. And the null space of that matrix is supposed to have some useful information about the kind of like the set that you started with. So in the example that we were discussing, let me see if I can draw it. I can find it here. So again, in that example that we were discussing, I had kind of like a generalization of a graph, which is going to be called a simplicial complex. And in fact, that's more as what I'll do for today. Just kind of give you the definition of what a simplicial complex is, how to recognize it, maybe do some examples, and then next time I'll also continue with some more like interesting applied examples. So that you kind of like get convinced that they are like interesting objects to consider. But okay, but for now, you can just think about it as some sort of like generalization of a graph in the sense that what is a graph? It's something which has nodes or vertices, right? And edges. So a simplification complex essentially, in addition to that, is allowed to have something kind of like of higher dimension. So in this case, the idea is that the higher dimensional piece is kind of this triangle that I colored in the picture, the solid triangle. Um, okay, and in this picture we had the one triangle, which is kind of like two-dimensional. We had five edges, right, which are the ones that you see there, and we had four vertices. And again, for now, I'll give you the definition in a moment. I'm just ordering the edges, like you label the vertices arbitrarily, and then it is once you have chosen an arbitrary convention for how you call which node, given in which node, then one way to refer to the edges. Is kind of like to draw an edge going from, a vertex to another, but starting with the lower value, with the lower index. So like in this case, when the edge has like the vertices B2 and B3, 2 is less than 3, and that's why I'm drawing it as being like an edge from 2 to 3. Okay. So that is kind of like the object we were working with, and again, like what we will do when we analyze these simplicial complexes for today is kind of like you think of it as being built out of pieces of different dimensions. So kind of like the triangle with the edges and the vertices. Okay. And then to define the matrices, you define the matrices, matrices are defined on vector spaces, if you think of them as linear transformations. So the vector spaces, in this case, there's going to be kind of like one vector space for one of these like categories of objects. So for the two-dimensional stuff, there's only one triangle. So the vector space that we would look at is just like one-dimensional, which is just like the number line. But for the one-dimensional piece, which is like five edges, so because there are five edges, so instead of working with R, you work with R5, so one per edge in a sense. And because there were four vertices, which is like the vertices are kind of like the zero-dimensional part of the structure. Then there are four vertices, so that gives you R to the four. Okay. And again, the idea is that kind of like a basis for each of these vector spaces is given by the corresponding geometric object. So like because it's an R5, like a vector, you kind of like think of it as kind of like where do I have this here? So on R5, uh, the the vectors are kind of like linear combinations of the edges, so which is what I mentioned last time. It's kind of like called like a formal sum because it's in the same way in which when you have I, J, and K, when you add them, you just leave it as plus plus plus, and you don't merge I with J into anything else. So it's kind of like the same here. Um, so um, so the way these two matrices were constructed, which is more or less the way they will always be constructed, is that they kind of give you the boundary of they give you the boundary of the object in question. So for example, for the matrix B, right? If I'm looking at the matrix B, I have to define it on the basis. In this case, like the basis is just a triangle. So I have to say what I want to, what is the matrix supposed to do to the triangle. So essentially, in that triangle, it's supposed to kind of like compute the boundary of the triangle. So like the edge, like the edges of the triangle. So a triangle has three sides. That's why you see some of three things here. It's just that the sides are kind of like counted with signs. So in this picture, I kind of was moving like counterclockwise. So you just check whether this, as you move along the triangle counterclockwise, whether you're traveling through the edges in the same direction that I have already like given them like a direction. For example, if 0, 1 is consistent moving counterclockwise, that's the same as E1, 2. That's why these two carry plus signs. But when you go back to where you started, you have to go against E0, 2. So you are going in the opposite direction. That's how I oriented this edge, and that's why the minus is there. Okay. Um, and it is actually connected in multivariable calculus to line integrals when you were computing work and things like that. So for example, if you remember like if you thought like, oh, you had like a triangle and you got a vector field and you want to find the line integral or the work or the circulation along that triangle, you would have said, well, you can work along the first edge plus the work along the second edge. And depending on how that's oriented, there might be a minus or a plus. So that's why in fact, this is very connected to like all these like multivariable calculus stuff. So once we have more things in place, we can go back to it. But it really interacts well with all of that. Okay. So, but again, like the idea is that each of these matrices is kind of like defined in the same way, which is kind of like trying to compute, is trying to kind of like find the boundary of the object. So the boundary of the triangle was three edges, and and just to go back to the just to go back to the previous page, the boundary of each edge, well, they're finite segments, right? So like it's just like the endpoints of the intervals. So again, the idea is that the endpoints are kind of like counted with sign, just kind of like a sign count of things. So in this case, like the convention is nice because it's just like the vertex with the higher index minus the vertex with the lower index. That's how we oriented that. Okay. And it is similar. It's that like this having like these things with signs is convenient in the same way in which why the integral is convenient to say that it's a sign area. It is nicer to allow positive and negative contributions. Because that's why that gives you a possibility that when you multiply the matrices together, you get something that gives you 0. Because if everything were positive, when you do matrix multiplication, if all the entries are positive or not negative, you're never going to get the 0 matrix. So you do have to have like negativity, to have the product of two matrices being the 0 matrix. The moment they're non-zero coefficients. Okay, and we'll come back to that later after I have given you the definition of what a simplicial complex is. But yeah, basically, kind of like the fun part is that once you have these matrices A and B, then you can find this Laplace matrix, and the dimension of the null space kind of like counts the number of holes in a sense that the space had. If you think about it as a space, so if you thought about it, kind of like you live in this weird world which is made out of a triangle with these two edges, and you can only move in that world. you know, then in the end, that there is kind of like sort of like a hole here, which is like an empty triangle, hollow triangle that you see there. The other one is filled out, so there's no hole there, and you can kind of like swing or move around, right? But for the other one, there's kind of like some like a hole there because it's not part of the space. So kind of like the way this will work is that the null spaces, the dimensions of those null spaces count those number of holes, but they can be of higher dimensionality. So not just one dimensional holes, but also like analogs of those. But before we get into those like examples or the details, what I'm wanting is just like the definition of the simplicial complex. Um, because I would be like basically like what we'll work with like for the entire course. And there's so many things that can be represented by a simplicial complex. So I do want to kind of spend some time in showing you how many natural things can be read in that way. Is that okay? Okay, so first I'll give you a definition, um, a definition that's useful as well outside of this context, which is called like a convex set. And then we can talk about a simplex and then what is a simplicial complex. So kind of like the idea for today would be to kind of like talk about convex sets. And then once you know what a convex set is, then we can talk about a simplex, a standard simple, like just like once like a standard simplex, let's call it like that. And then once we know what a standard simplex is, we can construct a simplicial complex. So it's kind of like, like the idea that the complex is kind of built out of the simplest. The standard simplex is kind of like Lego pieces. So the standard simplex is kind of different Lego pieces, which you kind of like assemble together into what you would call a simplicial complex. The convexity is a kind of like a term that appears in many different areas in mathematics. It's a very useful concept. What a convex set is, so if you take linear optimization or in many optimization problems having convexity is like a very useful condition. And it's also like a very natural definition, like to explain, very simple way to say what a convex set is. So okay, so what is a convex set? So I'm going to pretend that the set is kind of like just some region, like a subset of Rn. Okay, so you have like a subset of Rn. Well, not, like, let's just call this x1, x2, up to xn. So, in dimension n, and then you have a subset. Well, actually, this is not going to be convex. Let me try to draw something that kind of like will look a bit more convex. So I'll have a subset K. So this K is going to be a subset of Rn. And kind of like the idea is that a subset of Rn is called convex if whenever you choose 2 points inside the subset, the line segment, the connection is completely inside the subset. So if I choose 2 points, which I'll call P1 and P2, maybe I'll think about whether the notation is good or not. So, if I have 2 points inside the subset, for it to be convex, it must have the property that the line segment, or like the interval, if you want to think about it as an interval, whose endpoints are those 2 points must be inside the subset as well. So a subset is convex whenever if it has a property that a subset K, right? It's called convexity if it has a property that whenever 2 points are in K, the line segment connecting them is also inside K, also belongs to K. Okay. And so, like standard examples of a convex set, like I'll just draw some on R2 because it's easier to draw like the pictures. So like, let me show you some pictures if you haven't seen this before. So for example, a disk is convex. So some of these proofs, actually, if you want to show them, like they can get tedious, but visually, it's not like plausible that the disk would be convex, for example. So that's okay. So a disk would be convex, let's say. A triangle would also be convex. That would be useful because, um, in a sense, like the simplest will be generalizations of a triangle, and I'll explain what sense in a moment. But so a triangle like this one would be convex. Triangle. And so these are examples, and non-examples are super easy to come by, like almost everything is not convex. Because like, you can even take a disk, right? And it kind of from this more topological perspective, if you imagine made of rubber, just push it a little bit down, right? You push it down a little bit, now you have that. And now you have an issue because you have these 2 points, right? And if you try to connect those 2 points with the line segment, that takes you out of the disk. So it's super easy, very easy in practice to come up with non-convex sets, like the majority in a sense, like would be non-convex. Like convexity is like a very special property. Um, so this is like another example. And then another we will need this definition, like I don't think we'll use this per se, but it's still worth mentioning it so that it connects to other things you may have seen before. You can also define convexity for functions, which is useful. So you can say that a function is convex if its epigraph is convex. So I'll tell you what an epigraph is in a moment. So a function is convex. I won't use this too much, so I'll just kind of like draw some pictures. A function is convex. Epigraph is a convex set. So the epigraph is just at the points that, you have the graph of a function and the epigraph is just the points are on the graph or above the graph. So the epigraph consists of the graph of the function together with the points above it. So for example, again, like just to give you an example and a non-example. So if you take y equals x squared, if you take y equals x squared, like the standard parabola, then the epigraph is all the points on the parabola or above the parabola. So here you have to imagine that this is gonna go, that the parabola goes on forever. But the epigraph kind of like corresponds to all the points which are above the graph or of the graph. So that's kind of like the epigraph in the picture. So the epigraph, in this case, again, you can kind of like show that is convex, a convex set. So this one is convex. But if you take the upside down parabola, that's a nice example, and just contrast it. So if you do minus x squared, right? If you do y equals minus x squared, if you do that, then then still the epigraph are the points above the this parabola. Parabola, so it would be something like this, right? And you can kind of see that does not come back, right? You just like choose, for example, these two points, choose these 2 points. There you go, like the subside the epigram again. So this is not convex. So this one is not convex. The function you would say that y equals minus x squared is not convex. That making sense? In fact, the functions that are called convex in Calc 1 were like the ones that you would have called concave up, the one if the function is differentiable and all, with some extra assumptions that you can take second derivatives and all these other things. But if you look at y equals x squared, it's one that you would have called like a concave up function, right? And y equals minus x squared is concave down. So convexity is a good way to remember this. It is related to this concave concavity, like the concavity being like up. But it's just like a generalization because in fact you can, um, related to concave functions. It's a generalization, I guess, because, like, for example, absolute value of x, if you look at that graph, the epigraph that will still be convex, but absolute value doesn't have like doesn't have a second derivative at the origin or a first derivative at the origin. But at least when the function in Calc 1 was concave, had always like a non-negative second derivative, then the graph was convex. And that is the reason why it is useful when you're working with optimization problems and things like that is that convex functions, if they have like the minimum, is like an absolute mean. So it's, and especially in these like, machine learning problems and things like that, where like if some of you are interested in that, where you want to show like when you do gradient descent to minimize like the error function and things like of that sort, if you can prove that the problem that you're working with is like the function is convex, then when it's easier just to have like methods that show that the problem converges because you don't have to worry about getting stuck in a local mean and things of that sort. So convexity is like a very desired quality to have because convex functions, if they have like a mean, is going to be like an absolute mean. So there are no local minima. And there are in fact no local max, there are no saddle points, it's just like like a local mean. So convex functions, if they have I guess they could, if it's supposed it could be not bounded, but if they have an absolute local mean, it will be in fact it is in fact an absolute mean. So all these annoying things about worrying whether did you find an absolute mean or not, like they kind of like go away, and there are no max like local max nor saddle points. So it's worth I think mentioning so that you know that there's like a useful property to have, but like it's not that we're going to use this condition of convexity too much except for like what I'm about to tell you about. So when you have when you have some points, so if you have like a set which is not convex, there's kind of like a way to convexify it, which is called the convex hull, so if you have a set, I'll call the set S. Which for us, like, we're kind of like starting with a finite set, but it can be infinite in this case. If you have a set S, which is not necessarily convex, there is a way to convexify it, or kind of like create a convex version out of it. So there is a way to convexify it. Convexify. I guess convexify is not a word, but I think it would be something like that. That is, in a sense, I'll kind of write the formula in a moment, but it's kind of just better to just do like a picture first, like inductively of what kind of like what's happening first. So imagine that the set can only be 4 points. Okay, the set may not going to be convex at all. So kind of like the first kind of like step, if you want to think about it kind of like as a recursive method, like kind of a procedure, is that you can kind of like imagine, if you want to do this constructively, you could imagine just drawing like the segments, the line segments between all the possibilities, right? Like all the vertices with all the other vertices. So like you can think of that as kind of like step one. So, well, I'll distinguish them by calling this like, so this is kind of the originals, the initial stage, right, of the set, where it's just like the set first. So this is like step zero, meaning that you did nothing, right? Like, so this is like the initial data. And then step one would be kind of to draw like these segments that I'm telling you about, you know. So like from this vertex, all the possibilities. So from each vertex to any other vertex, you draw the line segments. And then from, let's see. Right? And then you can like draw these line segments. Step one, draw the line segments, connecting the vertices. And you kind of maybe see where I'm headed. Like you want to kind of like fill that in, right? Like if you were to, you kind of almost have like the skeleton or like the structure for what the convex set should be. Just like imagine pouring in some water and filling it in. So I mean, like the more precise way of doing that is like, and then you kind of like now iterate, right? Like now you take you draw all the possible line segments between all these things, and that kind of like in this case, like that's enough to fill it in, right? So like you just apply this same step to what you just found. So now you apply the process again. Of course, there's a formula which I can just write, but like it's kind of like nice to see first, like how it looks like, pictorially. But you of course can write it just like as a formula, which I'll do in a moment. If step two is coming, I'll do it again. And again, if you take linear optimization, you kind of like do a lot of this because the simplex method, if you have that before. Okay. There's your convex set. So of course it's like a big replacement, right? Because like you started with the finite 4 points and the convexification or the convex hull, like it's like this case it's kind of a two-dimensional thing, right? So and you're portraying it with something much larger, but kind of like it's still the convex hull is still kind of like determined by the vertices, like so it's kind of like the data of the vertices in this case does determine like the set itself. In fact, if you had like some points, so the idea is like kind of like the way to think about it is kind of like you can think about it in probabilistic terms because like for example, this point which is kind of like the midpoint between these two vertices, it's kind of like a, well, I just said it, right? It's zero, like the midpoint, so it's kind of like a combination of these 2 points, but where each point is contributing half the amount because it's in the middle. And then like, for example, like this one, which is kind of like looks in the center, it's not quite the center, right? But it's kind of like more like a contribution of the 4 vertices. So you kind of like take kind of like all the possible weighted averages of the vertices, like by weighted average, it just means that the coefficients add up to 1, so that you remember that one's probability. And then that is what creates a convex hull. So it has, what's nice about it is that, all these that's kind of what's going to be nice about the simplicists is that they have like a very geometric flavor, but at the same time very combinatorial and probabilistic flavor. So you can kind of like go back and forth between thinking about them in a more like combinatorial way versus thinking about them in a more like you know um geometric way. So if you have some points P1, P0 up to Pk, right? If you had if P0, P1. Oh, that actually because I called the set S. So let's say that the set S have been S0, S1 up to Sn. Okay, because again, you can most for our examples, we will always start with finite sets and then we will do things to them, right? So the convex hull of this set would be just like this thing that I was saying. Convex of S, sorry, that's how you write it. Where here, the sum of the PIs is 1. So that's why I'm calling the coefficients PI because you can think of them as like being probabilities. Oops, sorry about that. And it's very easy to kind of check that, any convex set containing those 4 points, we have to include all of that, and that thing is basically, already convex because you're taking these linear combinations that add up to 1. So it's not too bad to kind of like check that directly. We know that that would be convex. Okay, so we doing so far so good questions up to this point. Yes.
Sir, where does the P come from?
Oh, the P's are just like, I'm just, they're just coefficients in front of the elements, so I'm just calling them P's for probability. Because I do want to think of them as probability, like, kind of like what I was saying, in the midpoint case, it would be 0.5, 0.5, right? When you're taking the midpoint of 2 points, like, and so on. So, yeah, that's where like, they're coming. But of course, you could have called them anything, but it's just because that way they have like this very nice geometric, probabilistic flavor as well. That way. Um, So it's kind of like all the possible, another way to think about it is that it's like all the linear combinations that you can take of these points with the condition that the coefficients are non-negative. Oh, and I should say also that they're non-negative, so maybe, uh, right, because if I was calling them probabilities, I do want to think about them as being non-negative numbers, but it's not explicitly stated so far. So another way to think about it is that, yeah, you take the linear combinations between all the possible linear combinations between the points, but the coefficient must be like non-negative and add up to 1. So of the points S0, S1 up to Sn, uh, with the condition that the coefficients are non-negative, then the coefficient and add up to 1. So yeah, the weights are probabilities. So the weights are probabilities. The coefficients are probabilities. Can be interpreted as kind of like the probability or the amount that you use 1 point in building the point in the comments. that makes sense, of course. Okay, so that was enough like of a detour for convexity. Now, what is the standard simplex? So the standard simplex is just like the convex hull of the basis vector. So like the standard basis Euclidean vectors from Rn. So that's the next step. So the standard simplex. Oh, and then well, I'll write it in a note. So what is the standard simplex? Or the standard simplex is because there will be actually several, one for each dimension, you know. Also, the first one, you know, let me draw some pictures first, and then you'll see uh, how they're supposed to operate. So delta zero is just going to be well, first the way it would look like is just a point, which I'll just think of being the element one inside the number line, inside R. So that's kind of like just like the extreme case, because it's just like a point. Of course, a point is just convex. Like, so I don't have to even say anything about convexity. Delta one is going to be that line interval from 0, 1. Oh, actually, well, I guess whether I call it 1 or 0, it doesn't matter, I suppose. Like I could have called it 0, like it doesn't, just has to be a point. Just, and that doesn't matter what it is, so just it's a singleton, you know, so there's any term basically works. You know. But it starts getting interesting once you have at least another point, because then like the next standard simplex is that corresponds to this the interval 0, 1. So the interval 0, 1 inside R. Which in this terminology that I'm using, you can think of it as a convex hull of 0 and 1, like the sign. So this was like delta 1 was the convex hull of the set 0, 1. Okay. And then delta 2. So the you'll see in a moment kind of the number, the index is telling you the dimension that this is supposed to have. So delta 0 has 0 dimension 0 because it's just a point. Delta 1 is an interval, so an interval is supposed to be one dimensional. So delta 2 is supposed to be two dimensional. So in fact, I'll draw it in the already in how it's supposed to look on R2. So if you have the XY plane, it will look like the standard simplex looks like this solid triangle. It is solid, so it does include the inside. Otherwise, it wouldn't be convex. And you know, so that's how. And again, this is like the vertices are 0, 0, 1, 0, and 0, 1. So you can think of it as being the convex hull of the origin together with the standard basis vectors E1 and E2. So that's one way to write it down. And then, oh, the last one I can draw is delta 3, which is a tetrahedron. So like that's going to be in 3 dimensions. After that, you need like more, you know, you're done, like in terms of the pictures. But you can kind of like see where I'm headed, right? So delta 3, if you draw this in space, in 3D, so this is 1 0 0 0 1 0 0 0 1. And again, it kind of like looks like some sort of a pyramid, but it's called like a tetrahedron. So, and again, if I try to color it, the picture looks too messy, but just imagine that the inside is also is filled in, right? So the interior is included. So like filled in, or like a solid pyramid, if you want to call it that as well. So it's generally three-dimensional because again, you can go on towards the inside. It's not just the faces of the pyramid. And you know, what is that? It's a convex hull of the origin together with the E1, E2, E3 or IJK. Um, and as you can imagine, what is delta n is just the convex hull of the zero vector together with E1, E2, E3 up to En, like you know, in dimension, like inside Rn. So, but well, I'll say this in a moment. Maybe you already are noticing this, but they are determined, like, you know, if the filter tree is actually determined by 4 points or 4 vertices, you know, the two is determined by three, so it really, you know, it's n-dimensional, but it has n+1 vertices or like points that like determine it. So like, you have to keep track of like that, there's always like a difference of one in all these things, because you have like, if you have 5 points, you can build something for like dimensional, if you have 3 points, you can build something two-dimensional, and there's always like the dimension is always one less than the cardinality of the set. I'll write it down in a moment. So delta n would just be inside Rn, and it is just the convex hull of the zero vector E1, E2 up to En. But so in a sense, these are kind of like natural generalizations of a triangle. They're kind of like higher dimensional versions of a triangle in a sense, right? Because if you think of it like a pyramid, it's kind of like a solid version of a triangle, like a 3D version of a triangle in some ways. So, you know, like, you know, kind of like as a mental picture, you know, as a mental picture, like these standard simplices are like the higher dimensional analogs of triangles. It says. And what I was saying is that, you know, the dimension of one of these standard simplices is n, which is the number of vertices, right? -1. So there's, as I was saying, there's always like a difference of one in these things when you're like describing them. That's why sometimes it's convenient when they index to with the index to start at 0, because that way, you know, the last vertex is has n, so that matches the dimension. So that's the main reason for like indexing things that with 0 instead of 1, like at the beginning. Okay, and then okay, so basically now I can give you like the definition of a simplicial complex more or less, but kind of like the way to think about a simplicial complex. Again, there's always like all these things kind of have like two sides of the same coin, which is like there's kind of like a combinatorial aspect to it, and then a more like geometric aspect to it. So from the more geometric perspective, it's like a simplicial complex is you kind of like take a bunch of simplices potentially of different dimensions, and you imagine that you have like some glue, and you just like start sticking them in. Of course, and you cannot just do it like crazy, but there is some way to do it. It is kind of like a bit easier to kind of just define them combinatorially, and then you kind of like do the pictures to go along with it, but never worry too much for our purposes. Like the pictures just kind of like as a visual aid, but you can always work with them at a combinatorial level, and that is kind of like more reasonable. Also, if you want to use this for like data science applications, things like that, where like like the data it's kind of like the geometry is kind of like a bit of an abstraction, right? Because like if you have like a network, like the network could be of friendships or like other sorts of connections. So it's not that there's like it's not that that looks like anything in particular, but you just draw it in some way that it's useful. But kind of like at an intuitive level, like a simplicial complex, geometrically should correspond to simple to several simplices of maybe different dimension glued together in some way. Okay, and but again, we will describe them more like at a combinatorial level, and they just use the pictures to motivate like the idea behind them. But the combinatorial description is very straightforward. So we'll define them because it's just easier to work with them that way. So, if this were like a more like advanced class, I'm trying to keep things like as simple as possible. You would kind of like prove that every of these combinatorial definitions has like a geometric version, which is called the geometric realization of the simplex, so that it can be realized as a geometric object. But like it's not for our purposes, it's not like a very interesting thing to do. But it can be shown that if you have like a combinatorial object, you can really literally can think of it like you are allowed to think of it as a geometric thing. But for us, like we'll just kind of like take that as for granted, but it is possible to show that. So okay, let me give you let's do it first with the example I was mentioning last time. And I'll explain why that is a simplicial complex from our perspective. Okay, so let me see if I can copy paste a picture that I had from the notes from last time. Okay. And in fact, because it's combinatorics, right? In combinatorics, there's no direction. So like I will even drop down the letters to just sorry, the orientations or like the arrows, so that you don't think that that's kind of like part of the definition. So it is going to be very much kind of like almost like a list of like information. Okay. So I'll just try and make this. So this again, this was the example that we had. So again, you can kind of like think about it as being described kind of like level by level. So at the most basic level, you have zero-dimensional data, right? Which are like these vertices, right? So yeah, I hate my send notation, but I'll put kind of each of the vertices as its own set. Okay, because this set is supposed to represent just one of them at a time. So, so again, you really, and in fact, when I show you once we talk about the boundary and all this stuff, I'll show you how to compute some of these things on Sage or like, Julia or Python, whatever you want to use. And when you enter the code, you literally just give a list of numbers, like, that's what you write down. So I'm trying to write it in a similar way to how you would write it then when we talk about how to put it on the computer. But, okay, so you have the vertices. Um, And then you have the edges, right? So to refer to the edges, again, because it's kind of combinatorial data, there's no geometry. So I just refer back at the edges in terms of like that kind of like you have to think that the edges are determined by their endpoints. So you just refer to each edge as a list of two numbers, or vertices, which vertices their endpoints. So in fact, you don't even write this notation, but you just write V0, V1, comma V1. So basically the edges are represented in the simplicial complex this way. And again, these two element set is a standing for the edge. So this is meant to represent the edge. But again, the edge itself as a curve or like a line segment is a geometric thing. It's not something discrete. So the thing is that you kind of like represent all of this information by discrete data. So basically each edge is represented by a two element set. So and it's super easy to kind of like identify them because it's just like in terms of their endpoints. So that makes sense. And then the triangle is not only the same, in a sense, the triangle is determined by the edges, but the edges are determined by the vertices. Like the triangle, is determined by its vertices. That's kind of like the point of the complex form stuff. You only need to know the vertices to determine it. So to refer to the triangle, you would just list the three vertices that make up this triangle here. So it would be V0, V1, V2. There are the one that uh, and then the triangle. So here I'm just telling you how you kind of represent as a list each of the objects. I still haven't told you why this is counts as a simplicial complex, right? I'm just saying this is kind of like the translation that you would do or like referring to these things. Okay, so that makes sense. Okay, so again, I still haven't said what this makes a simplicial complex, but let me put, this is going to be one, but let me put next to it one that is not, so that it's easier to just tell the difference between them. So I'm going to draw exactly the same picture, but I'm going to delete this edge in the middle, for example. That's the only change I'm going to make, and you'll see that, okay, so again, this will be a simplicial complex, will be. But the next one is not going to be one. So I'm going to basically take the same picture. Oops. I'm going to take the same picture. Well, I just need some time to process things. Yeah. So I'm taking the same picture, but again, the only change I'm making is deleting that edge. Okay, so in the combinatorial description, the only thing that you will delete is like that edge that corresponded to this third side, which would be V0, V2. Right? Well, you know, So like from a geometric perspective, it's maybe kind of a bit more clear, like what's happening, right? Because you kind of deleted one of the sides, one of the faces of a member of the triangle. Uh, but kind of like as a list, right? How is it that you would what is that problem that this has now as a list of like as a collection of subsets? So the issue now is that if you look at this triangle, now not every subset of this three element set is part of the simplicial complex. So essentially, what a simplicial complex will be is something that is closed under subs inclusion. I'll say what that means in a moment, but basically it just means that if something is in a simplicial complex, every subset you can make out of it should also be considered as being inside the simplicial complex. So the reason this one is not, the reason why this won't qualify as a simplicial complex is that, the three element set, which is B0, B1, B2, right? Has a subset, which it would be B0, B2, the one that I deleted, right? Which is no longer in the list, which has not, is no longer shows up in the list, which is no longer in the list. In the list, that determines the complex. So again, kind of like and that's kind of going to be the combinatorial definition of a simplicial complex. It's just going to be a bunch of subsets of the of the vertex set. But with the property that if one set is inside this list, every subset of it must be part of the list as well. So kind of like all the smaller pieces, kind of like the faces, or like like the edges, like the vertices, all of it. If you have something of higher dimension, every small thing that you can kind of like extract from it must also belong to the complex itself. Uh, so kind of making sense, like the distinction between the two cases. Uh, and then I'll give you a more like kind of like a socially science like example, so that you see like a distinction as well of like like if you wanted to use this to model other situations, and then next week I'll give you more like interesting examples as well. But kind of like the idea of a simplicial complex. Okay, so our the definition of a simple definition. Or a simplicial complex, let me write it like this. Consists A simplicial complex consists of subsets let's see, used from
Does this mean every simplicial complex must be a power set?
well, that's the thing, like it's not necessarily a power set because you don't have to put like all the subs, like for example, I didn't put actually I also make that side a remark because it's like a good point as well. In the power set, you really have to include all the possible subsets, right? But here, like this one, right? Like it's not part of the simplicial complex, the way I described it, because there was nothing three-dimensional in the simplicial complex, right? Because this kind of corresponds to a tetrahedron, if you think about it. So to answer your question, no, it's not because then like it would kind of like not be as interesting. So it's just that the moment there is a subset, every subset of that must be within it, which is a little bit different than saying that every subset, of the vertex set. Well, yeah, okay. Let me put it more like kind of like recursively. So for simplicial complex, you have this vertex set, okay? or yeah, because that's a good point, and that can be like, for simplicial complex, you start with a vertex set. And the vertex set is just going to be called V, like, let's call it V equals, V0, V1, up to VK. I won't call it VK because I don't want you to think that it's necessarily of the highest dimension possible. So the idea is that, okay, so the idea is that every vertex, every single, so the conditions for a simplicial complex are the following. Every vertex V sub I is part of the simplicial complex. Simplicial complex is just a list of subsets of this vertex set. Right. I need to master this stupid app because sometimes it doesn't let me like edit when I try to. Oh, I think I know what I understand. Yeah. A simplicial complex is a collection, is a list of subsets of the vertex set that satisfies the conditions. The first one is just that every vertex is considered part of the simplicial complex, so every vertex must be listed as part of the simplicial complex. So every vertex must be listed, must be in this list. And the second one, which is really what makes it like an interesting definition, is this closure condition, which means that if a subset was listed, or if a subset appears in the simplicial complex, or let me call it set, because otherwise it's a set is if a set appears listed in the simplicial complex, then every subset of it must be listed as well. So note, just as a remark, this does not mean remark. This doesn't say that every possible subset of the vertex set is in the simplicial complex. Remark. The, the closure condition does not mean that every subset of the vertex set is part of the simplicial complex. So if you have seen like this before, like about the power set, this is saying that it's not necessarily the power set of the vertex set. So it is not necessary. The power set of a set is just like the set of all subsets of it. It's like a definition that's not too important for us in the moment. So like, it's kind of more like a remark for those who know that terminology already. Okay, so let me, is that kind of making sense? Let me finish with an example, which is kind of more like, again, more like the social sciences, so that you see how this could be used like in different contexts. And then next time I'll give you more interesting examples. But here's like a, here's here's a fun example because again, it's not necessarily something you would think about it at first class. So you could think of the vertex, here's an So you could think of the vertex set as being represented by, you know, all the professors at a university. So like the vertex set would represent all the professors. Okay. So that's kind of like the list that you start. Okay. And then just to keep it simple, you would say that you would include a subset of consisting of two professors. I'll call them P1 and P2 for Professor 1 and P2, Professor 1 and Professor 2. So let's say that they're like K, you know, they're like K plus 1 professors. Well, that I won't call them like anything. All the professors at a university form the vertex set. Okay. And then you want to say that the two element set P1, P2. So this is kind of like a set making up of the two professors. You would say that you want to say that that belongs to my list of the simplicial complex if they have co-authored a paper. You know, so if I wrote the paper and they are like the two authors of the paper, if they are the two authors of a paper. Okay, belongs. Okay, and again, you can imagine that already that gives you a graph, right? And you have like all these professors, and you could draw a graph, just connect them with an edge if they have co-author a paper. That's already enough to determine a graph. So the point of a simplicial complex is that it is meant to understand relations which are not just binary, right? Because something like a co-author in a paper is just of two people, so it's a binary relation. So the simplicial complex is a way to kind of like capture ternary relations, like meaning three people, or like what would be quaternary relations, like, you know, for four people, or like whatever, like the name is for the higher ups. But you could include as many like more complicated networks that you want. So like for example, just to make this no longer a graph, you could say that um you would have if you have an element set of three professors, right? Like a list of three professors. P1, P2, P3 would belong to the simplicial complex if the three of them wrote a paper together. Okay, if the three of them. So again, pictorially, if they're like three professors and they're like the authors of a paper, you would draw. If you want to think about this geometrically, you would draw a solid triangle. You know, so maybe let me draw like a, you know, like, so the situation could be you could have like a very simple small university where there's only 6 professors. So let me not make anything too crazy. So, you know, like these three wrote like a joint paper. So you represent that pictorially by drawing a solid triangle. Okay. Like maybe Professor Five never wrote a paper, so they are alone, so their own island. Which is my number 6 in this case. I think this is what I'm calling 6. So, and then, you know, like Professors 1 and 6, they did wrote a joint paper, so they are connected. Okay. And Professors 6 and 4, they wrote a joint paper, so they're connected. And let's say that two are Professor 2 is like here actually. That should make it professor. Okay. Okay. So now with the closure relation sets, and which is not super clear but that's why I wanted this example because it's easier to understand. So in order for this list to qualify as a simplicial complex, it must be the case that if three people wrote a paper together, then pairwise they also wrote a paper together. That's what the closure means, that every subset. So it's not something that would always happen, right? Because you could imagine a situation where three people wrote a paper together, but it's not that then they had like their separate papers where they just did it pairwise. But that's what the closure relation says, and that's why I'm kind of like drawing like all the sides here, because that implicitly is saying that P1 and P2 wrote their joint paper, the P2 and P6 wrote their joint paper, and P1 and P6 wrote their joint paper. So that is why the closure relation is like a strong condition, because it is forcing kind of like binary relations among the members. So it's saying kind of like if there's like a larger relation in the group, there's also like a smaller relation between the subsets of the group. So kind of like kind of like a domino effect, it propagates throughout the group. So it's kind of like in a group of friends, maybe friendship is like a better example of something that's more naturally like a simplicial complex, because you have if you had like a friend group, I mean, you kind of like maybe expect everyone to be friends with each other, and maybe in triples, like it would be weird if three people hated each other and then you are like in a friend group of four and you still call yourself like a friend group. Like there's kind of like so that like the friendship is kind of like a more naturally like a simplicial complex. But kind of what I'm trying to say is that the closure condition in plot means in this case that that if three professors wrote a paper together, then they pairwise wrote joint papers. Wrote joint papers. So from this perspective, yeah, what is what I was saying. So from this perspective, and the closure relation propagates kind of like a property throughout the smaller subsets. The closure relation propagates a property or relation across along smaller pieces of a region. Smaller populations. And so another example was this friend group example. Are there examples? Because if four people are friends, you expect them to be then the smaller subgroups of those four people should be friends as well. But that's kind of like, like that's kind of like the interesting thing here, where you kind of like start thinking, oh, there's like, in which circumstances is this like a realistic model for like a situation, like, for like but it's kind of like a generalization of like a graph or like a network, but this very strong condition of like propagation, But that is what makes it like a useful gadget to work with. The fact that it allows you to do this. I mean, yeah, probably I think I'll try to at some point talk about applications to signal analysis, and you kind of can build like a complex out of it. Like, if you have like detectors in a forest, and you want to know if they cover like what's the minimum number of detectors that you have to put in place to like cover, like, if there's like you have a network of sensors that may not be perfectly accurate, or like you don't know their coverage. No, like there are ways to go and do this in terms of visual complexes to answer those questions of like, what's the minimum number necessary to guarantee that you can detect any triggers like that. And so there are fun examples here, like kind of like here, and you just have to kind of have like a nice mindset to analyze it. But yeah, I'll mention some next week. But if we'll continue talking more about it on Tuesday. I think it's like a good place to end, because also we're almost out of time. You're unnecessary questions. Okay.